Hi class, we're going to look today at first section of chapter 4. We're getting into some quantitative chemistry, and so I want you to appreciate the real importance of numbers here. And if we were to look at this table, table 1 and table 2 collectively, we see some properties of different compounds that both contain the same elements. So carbon monoxide with one atom of each element and carbon dioxide with a 1:2 ratio of these elements clearly have quite different properties, melting and boiling points, densities, and their solubility. And then when we look at the symptoms of carbon monoxide poisoning, we realize the difference between these two compounds is quite significant. Carbon dioxide is certainly a poisonous gas, but not at that level, and certainly not with that risk of death. So the numbers of atoms of each element in a compound can really affect the properties. We see this in the introduction to chapter 4, where the compounds water and hydrogen peroxide are compared, and clearly their properties are quite different, even though they both contain hydrogen and oxygen. So in this section, we're just going back historically to two scientists who did work on chemical reactions, and Joseph Proulx and John Dalton both came up with similar conclusions. John Dalton is known for his law of constant composition, and Joseph Proulx, in this section, we find on page 162 a similar statement of definite proportions. His law of definite proportions is quite similar to Dalton's, but I've summarized Dalton's statement here, which is that a specific compound always contains the same elements, that's clear, and that the compound will always have the same percentages by mass or proportions by mass. So in the case of carbon monoxide, the proportion is about 43% to 57%, and in carbon dioxide it's a little bit more of a divide. It's about 27% to 73%. Now those numbers there, we could determine those percentages mathematically if we were to look at the periodic table. We'll get to that a little bit later on once we've covered relative atomic mass in this course. And then we can use the atomic masses from the periodic table to come up with those proportions for each of the elements. Okay, now this video is just intended to introduce one main branch of chemistry, which really sets the stage for the rest of our work in the course, at least in the quantitative chemistry. And it's this branch of chemistry called stoichiometry. And it's made up of two words. One is the word for element, and the other one is the word for measure. So we're looking at measuring elements, specifically their masses, or possibly their volumes if it were a gas phase reaction, or if the compound was in its gas phase. And the study of the relationship between specifically quantities in the reactants and products when we're looking at chemical reactions is what stoichiometry is all about.
Baking soda is a base. Vinegar is an acid. Mixing the two results in an acid-base and gas-forming reaction that releases carbon dioxide gas to the air. If we add more baking soda to the vinegar, the reaction continues. If we continue to add baking soda, however, the reaction diminishes until, eventually, no reaction occurs. Why does the reaction stop? Can we predict when the reaction will stop? Can we predict the quantity of CO2 produced by the complete reaction? We can answer these questions using a branch of chemistry called stoichiometry.
Okay, stoichiometry. An odd word, but in the Greek, element and measure are the two base words. So this word really sums up quite a lot of what we do in chemistry, particularly when we're looking at chemical reactions and we're considering reactant and product masses. So their quantities are really important. And in this branch of chemistry, quite often the masses of reactants and products might be based on liquid mass, maybe a solid state reaction, or it could be gas phase reaction, but it would all be called stoichiometry. And we'll see later on in the course, we'll look at gas stoichiometry, gravimetric stoichiometry with solids, and solution stoichiometry. In this case, we're going to just enter into this branch of stoichiometry really lightly in this first section, and the rest of your worksheet here, we're going to look at some practice questions from this section. The very first one, as all of them are asking us to write formulas to show the different combining proportions for the compounds of the following elements. So the connection here with stoichiometry really is that we'll have different ratios of ions in the possible compounds for these multivalent metals. And if we look at the law of constant composition, because of the different ratios, we'd have different percentages by mass, just as carbon monoxide and carbon dioxide each had unique percentages by mass. We're not calculating these percentages at this point, but we're just trying to come up with the chemical formulas, a little bit more practice with that skill. And in the first example I've shown for you here, we have mercury, which is a multivalent metal. It would give rise to two possible perbromate compounds. The one, which is the mercury 1 perbromate, and the second one is the mercury 2 perbromate. Mercury, its most common valence is 2, so in fact the mercury 2 perbromate, which would be this one here, would be the most abundant form of that compound. So for the remainder of this, just pause at the different intervals in the lesson, and I'll reveal the answers for those, and you can get practice with a little bit more of your polyatomic ions. So when we look at part B, this is gold, dihydrogen phosphate. Remembering phosphite is based on phosphate, and phosphate being PO4, 3 negative, phosphite is PO3, 3 negative or negative 3, and combining that with 2 hydrogen ions, we would lower the valence of the phosphite by 2. So dihydrogen phosphite has a valence of negative 1 when combined with gold 3. Would need 3 of those ions. It would be 3-to-1 ratio. Percentage by mass would obviously be a little bit more heavily weighted on the phosphorus and hydrogen and oxygen atoms than would be in the case where we only have one dihydrogen phosphite. So we can imagine there the percentages by mass would be a little bit closer to each other in the gold 1 compound. Okay, now moving on, in the next example here we have again a multivalent metal in tin, which has again 2 valences, the +4 and most common state, and the +2. Hydrogen sulfite, again the sulfite ion, which is based on sulfate with a -2 valence, so hydrogen sulfite would have a valence of -1, and then pairing that up with tin 4, we'd need 4 of those ions, and tin 2 respectively. So you can see that again there different combining proportions are going to have different percentages by mass, which is going to affect the mass of the elements or the compound in this case if we were carrying out a chemical reaction with tin hydrogen sulfites. In the last case, we have a carbonate, and we're looking at cobalt combined with that. So carbonate being CO3 -2, we would look at hydrogen carbonate as just reducing that valence by 1. So its valence is -1. And again, looking at the 2 possible cobalt hydrogen carbonates, we would have cobalt 2 and cobalt 3. And again, the ratio of cobalt to hydrogen carbonates is 1:2 in the first compound, and the ratio is 1:3. Now we're not suggesting that those compounds would have percentages by mass of 1:2 and 1:3 proportionally, but we're saying that the number of ions is going to be 1:2 and 1:3, so that would certainly affect the percentages. It's just a little bit of practice in the textbook for this section, so this is a small little lesson. Number 6, page 162, just discuss with a partner in class, and 7 and 1, make sure you complete those, and then tomorrow we'll be probably looking at starting in on relative atomic mass and isotopic abundance.